anticipated problem session problem after the next class. The equation that we have is 4 times x1 times x2 plus an x3 quantity squared. The way that starts is how many variables are there? x1, x2, x3.
3.
So an x1 variable, an x2 variable, an x3 variable, an x1 variable, an x2 variable, an x3 variable. And so if I think about multiplying them together, here's x1 times x1, that's x1 squared. Here's x1 times x2. Here's x1 times x2 as well. Here's x1 times x3. And here's x1 times x3. And over here that would be x3 times x3, x3 squared. So x1, x2. x1, x2 can come in here and can come in here. There's 4 of these. I'll put 2 of them over here, half of them over here, half of them over here. That's this guy. Then the x3 squared only occurs here with a single multiplier of 1, and everything else is going to be 0. So this problem reduces to, once you know how to find that matrix in Y, I'll call this the matrix A, the problem reduces to eigenvalues, eigenvectors, or A, and then first step, and then the last step is for the same eigenvalues. Do QR on the eigenvectors. So it puts everything you already know together. How to write that matrix, I'll explain in detail on Wednesday. It's pretty trivial once you see it. Once you know how to set it up, the rest of it is just this. So let's go and do this eigenvalue eigenvector. So step 1, here's my A, it's 0, 2, 0, 2, 0, 0, 0, 0, 1. Step 1, our eigenvalue problem. Anybody see them immediately? Square, square. Here's an eigenvalue.
1.
Rose it up to 2 in the other one. So 2 is an eigenvalue. And since the trace is 0, the last eigenvalue has to be minus 2. So you could read it off if you like. If not, you set out the problem. P of lambda, the characteristic polynomial, is the determinant of A minus lambda I is equal to the determinant of minus lambda 2 to minus lambda 0, 0, 0, 0, 1 minus lambda. Like this row over here, plus, minus, this is a plus sign, this is a minus sign, on the diagonal that's a plus sign again, this is equal to 1 minus lambda. By the way, anybody here that loses this parenthesis? Don't lose it. It's necessary. So 1 minus lambda times the determinant of this matrix, that's lambda squared minus 4. And so we see pull out the minus sign, minus lambda minus 1 times the square root of 4 is plus or minus 2. So lambda plus 2 and lambda minus. The eigenvalues, therefore, are lambda is equal to 1, minus 2, and plus 2, and the multiplicities going with that are 1, 1, and 1. So at this point, I'm ready for my table. And that table, by the way, has a couple of functions. First one is it summarizes your results in a place where you can find it easily, and where if you're careful about putting everything on the table, it reduces your mistakes. The other thing it does is, yours truly at 2 in the morning, still grading. If I find the table, and the table is correct, oh, it's just a quick glance that the computations are there, so that it makes sense, and oh yeah, that student is good. Right? If not, if the table is wrong, well now I have to go look, where's the mistake? Is it conceptual, or is it just arithmetic? Arithmetic, take off a point. Conceptual, ouch. Okay, so the table. It gets bigger now. The lambdas, and we had minus 2, 1, and plus 2. Minus 2, 1, and plus 2. I just happened to choose this order. Each one of these occurs once, and therefore my basis for E lambda, I know I'm going to find exactly one vector in each one of these. I can't find more than that multiplicity, so I know it's going to look like this. Now, let's look at that. So step 2, the eigenvectors. The eigenvectors, well, I have 3 cases over here. Case lambda is equal to always minus 2. So I want the basis for the null space of A minus lambda I evaluated at lambda equals minus 2. That is the null space of A plus 2. If I write it painstakingly like that, I'm winning at my sign mistake. If I didn't, if I mistakenly took A minus 2I and 2 were not an eigenvector, what would happen as you do the computation? You wouldn't have a missing pivot. So it's at that point that you would know that, hey, wait a sec, maybe I made a mistake. Lambda? I say if you somehow or other didn't write the correct expression, and you then do Gaussian elimination, you wouldn't have a missing pivot. So at that point you know to look for a mistake. So I have to take A and add 2 to the diagonal. That makes this 2, 2, 0, 2, 2, 0, 0, 0, 3. And if I do Gaussian elimination, I'll scale by 1/2, so I'll get 1, 0, 0. Second row, first row are the same, so I know I get rid of that one. That just leaves me this last one, and I'll scale it by 3. It's going to look like this after I do Gaussian elimination. I have a pivot here, and a pivot here, and a free variable. Missing pivot. Yes, I had to have a missing pivot. And I knew it had to be exactly one missing pivot, because the multiplicity here is 1. That can't be more than that multiplicity. So, choose that free variable. If I write alpha, I get all of them. Just let's make it easy. Let's just choose 1. Then the rest of the equations read that x3 is equal to 0, and x1 is equal to minus x2, and therefore I get that vector x1 is equal to minus x2 is minus 1, x2 is plus 1, x3 is 0. So minus 1, 1, and 0. Case lambda equals 1 comes next. Lambda is equal to 1. Null space of A minus lambda I when lambda is equal to plus 1. So A minus I. We subtract 1 from the diagonal. So minus 1, 2, 0, 2, minus 1, 0, 0, 0, 0. Okay. This goes like minus 1, 2, 0. This row minus 2 times the first row, we'll get rid of that. So plus 2 times the first row will get rid of this 2, so 2 minus 2 is 0, minus 1 plus 4 is 3, 0, 0, 0, 0. Here's my free variable, x3 is equal to 1. This one equation reads x2 is equal to 0, and that equation then will read x1 is equal to 0, and I get 0, 0, 1. 0, 0, 1 is a basic. Third one, plus 2. Plus 2, plus 2, minus 2i. Diagonal changes. So let's see, I had to subtract 2 off the diagonal. It was minus 2, minus 2. 1 minus 2 is a minus 1. So that last row I know will go to 0, 0, plus 1 when I scale. I'll have a missing pivot because this row is the negative of that one. So just need to keep 1 and I'll scale it by 2 to get 1 minus 1, 0. Yeah, it row reduces to that now the Gaussian derivation. If you get it wrong, you'll be in trouble, right? So either you are practiced enough so that you can do that in one fell swoop, or else you do Gaussian elimination slowly and make sure it's done. Okay, so here. Free variable, I'll choose it equal to 1. So x2 is equal to plus 1. Then this reads x3 is equal to 0, and x1 is equal to x2. And therefore, the x that I get out of here is equal to 1, 1, and 0. 1, 1, and 0. Okay. I'll tell you the result that you're going to get. The matrix that we have is symmetric. Whenever we have a symmetric matrix, the eigenvectors that we find for different eigenvalues are going to be orthogonal. Check. Are those vectors orthogonal to each other? Yes. Okay, so when I did this very quickly, I knew that I had a check that I could do. Do those vectors that I get for the different eigenvalues, are they indeed orthogonal? Yes or no? No. So automatically, these guys, this one and that one, don't work to 0, this one and this one don't work to 0, this one and this one don't work to 0. In here, for the same eigenvalue, those are eigenvectors for the same eigenvalue. Right? If I change them in that plane, they're still eigenvectors. So in here, I can do QR. And in here, I can do QR. And in here, I can do QR. And what will happen after I do it? These guys will be unit length orthogonal to each other, unit length orthogonal to each other, unit length orthogonal to each other. And they're all orthogonal to each other to begin with across the eigenvalues. I'll get orthogonal. I'll get IJK out of that. So that's going to be the result of that on Wednesday. What's QR for a single vector? What do the QR equations reduce to for just one vector? W1 equals V1, O1 down. Q1 is 1 over the length of W1. Means change